Hello friends, IBM is here with another episode of Learning Physics, and this is going to be a continuation of AS Physics multiple choice questions. That is, this is atomic structure and particle physics, AS Physics 9702 multiple choice questions. Part 1 would have been longer, but something happened to my machine, so that's why the video abruptly ended in part 1. But nevertheless, I want us to begin part 2 from where we stopped. I think in part 2 we must have stopped on page, I think it's page 7. Okay. We must have stopped on this question here. An unstable nucleus of an element decays by emitting an alpha particle or a beta particle to become a nucleus of a different element. The nucleus is also unstable and also emits alpha particle or a beta particle. The process continues until an isotope of the original element is produced. So I want you to note that it cannot emit only alpha particles if it is to become an isotope. If it emits only alpha particles, it means the proton number goes on decreasing. If it emits only beta particles, it means the proton number goes on increasing. Therefore, it must emit a mixture of alpha particles and beta particles in order to go back, because the alpha particle increases the proton number, yet the beta particle reduces the proton number. So if the nucleus X, let's say the nucleus X emits an alpha particle, let's say it emits X alpha particles and Y beta particles as shown by that equation, but the proton number of X and Y should be the same in this case. So if we equate the left hand side is Z and the right hand side should be Z plus 2x minus y, where we say that y is equal to x. That means for x equals to 1, y should be 2. For x equals to 2, y should be 4. In other words, the number of y particles will always be greater than, or will always be twice the number of x particles if the proton number is to remain the same. So let's say if x equals to 1, that is, if one alpha particle is involved, it means y is going to be 2. That means there will be 2 beta particles. And therefore, if x, this means the total number of particles is going to be 1 plus 2, which is going to be 3. If we say x is equal to 2, if x is equal to 2, it means the y particles are going to be 4. That means 2 plus 4 will be 6, and 6 is none of the answers here. So the smallest number is going to be 3 particles involved, that is 1 alpha particle and 2 beta particles. So the answer is going to be 3. The diagram shows the quark composition of 4 different hadrons. One of the hadron is sigma plus. It has a charge of positive E, where E is the elementary charge. Which hadron could be the sigma plus particle? So we just check the charge. This one is down, strange down. That would be negative 1 over 3e plus negative 1 over 3e plus negative 1 over 3e. The charge here is negative e. Down, strange, negative 1 over 3e minus 1 over 3e minus 1 over 3e. The charge here is also negative e because strange particles have charge of negative 1 over 3e. Up, strange, up charge has 2 over 3e. Strange has negative 1 over 3e, and another strange negative 1 over 3e. And I think the charge here is going to be 0. Then up strange, this is 2 over 3e plus 2 over 3e minus 1 over 3e. And the charge here is going to be 3, that is 4e minus e, which is positive 1e. So this is going to be the answer in that case. The table gives some data relating to 4 neutral uncharged atoms, W, X, Y, and Z. Nucleon mass number is given. Total number of particles, protons, neutrons, and electrons in the atom is given. So two of the atoms are isotopes. Isotopes should have the same proton number. Here they have given us total number of particles, protons, neutrons, and electrons in the atom. What is the proton number of this element? So the table gives some data relating to 4 neutral, that is uncharged atoms, W, X, Y, and Z. Two of the atoms are isotopes of the same element. That means they should have the same proton number and same same proton number but different nucleon number. So let's find the number of neutrons. This is nucleon number, then this is number of protons, neutrons, and electrons. So the difference here, if the total number, of course, if this is the nucleon number, the number of protons, remember, is the same as the number of electrons for a neutral atom. So the nucleon number, if the nucleon number is 16, it's the total number of particles, protons, neutrons, and electrons is that. So nucleon number is protons and neutrons. So let's find the number of electrons here. Is number of electrons is going to be 24 minus 16, which is 24 minus 16, that is 8. That's number of electrons here. It is also going to be the same as the number of protons. So the number of protons is also 8. Number of protons is 8, which means the number of neutrons is also going to be 8. So there are 8 protons, 8 neutrons, 8 electrons. So let's check, because the question is what is the proton number of this element? Two of the atoms are isotopes of the same element. So let's check this one. Number of electrons is 26 minus 17, which is 26 minus 17, which is 9. Number of electrons is 9, that is electron number. Number of protons is also going to be 9. So the number of neutrons is going to be 17 minus 9. 17 minus 9, which is 8. So this is number of neutrons. Okay. Then we can look at Y. Number of electrons is 25 minus 17, which I think is 18. No, it is 8. That is number of electrons, which is the same as number of protons. And the number of neutrons is going to be 17 minus 8, which is, 17 minus 8, which is going to be, let me first check, 25 minus 17, that is 8. Number of electrons is the same as the number of protons. This is protons, this is electrons, this is neutrons. Electrons are 8, protons are 8, so the neutrons is 17 minus 8, which is 9. Then for the last one, number of electrons is 28 minus 18, which is, so electron number is 10, which means proton number is 10 for a neutral atom. Then 18 minus 10, we get the number of neutrons, which is 8. So they have said two of the atoms are isotopes of the same element, so they should have the same proton number. And those elements with the same proton number are actually W and Y. They have proton number 8. So what is the proton number of this element? So the answer is 8. What is not fundamental particle? Remember, fundamental particle should not be made up of anything simpler. The electron is not broken down any further. The neutrino is not. The neutron is made up of up, down, down. It is made up of quarks. The positron is not broken any further, so the answer there is the neutron. An unstable nucleus decays and emits a beta minus. What changes, if any, occur to the quark composition of the nucleus? So if the nucleus X decays to give Y, so this is A, this is Z, nuclear number does not change, Z should increase by 1 if it emits beta minus 0, negative 1. So the proton number is increasing by 1. That means a neutron has changed into a proton. A neutron has changed into a proton if the proton number is increasing by 1. So that means up, down, down, change to up, down. So one down quark. What changes if n occur to the quark composition of the nucleus? So the up quarks, those ones are increasing by 1 because, and the down quarks are decreasing by 1 because one down quark changes to an up quark. So the up quark will be increased by 1 and the down quark decreases by 1. So the answer is going to be B. A radioactive nucleus emits an alpha particle or a beta minus particle, creating a product nucleus. Which decay could create the product nucleus stated? It emits an alpha particle or a beta minus particle, creating a product nucleus. So let's check. The first one is showing a nucleon alpha decay. Nucleon number is reduced by 4. Proton number has reduced by 2. Okay. The second one is showing that it is uranium 238.92. Oh, by the way, this is not true because an alpha particle is 42. 226 minus 224 is not 4, so this one is wrong. Uranium 238 alpha particle, so this should be minus 4. This should be minus 4, it should be 234 minus 2, it should be 90. This is wrong, it has increased instead. Beta minus, so this should be nucleon number remains the same, proton number increases by 1 because beta minus is beta minus is 0, negative 1. So when Ra 228.88 decays by emission of beta minus 0, negative 1, the new nucleus Y should have 228 and this should have 80. This should have 89. That should have 89. That should have 89. So that the proton number is balanced. That means this one is also not correct. Automatically, it means this is the correct answer. We can verify. TH 231.90 decays by emission of beta minus 0, negative 1 plus a nucleus Y. This should remain 231 and this should increase to 91, so that 91 plus negative 1 is 90, so that gives us the answer. Which statement is correct? Electrons and neutrinos are fundamental particles. Electrons and neutrinos are fundamental particles. I think that is true because electrons are not broken down any further. Neutrinos are not broken down any further. So those are fundamental particles. Electrons and neutrinos are hadrons. That is true. They are leptons. Protons and neutrons are leptons. That's not true. They are hadrons. Protons and neutrons are quarks. That's not true. Protons and neutrons are in other words, are actually the ones made up of quarks. They are not quarks themselves. The figure shows part of a chart of nuclides where the neutron number is plotted against the proton number. An unstable nuclide X decays by emitting an alpha particle. Which nuclide is formed by the decay of nuclide X? So they are saying X decays by emitting of an alpha particle. Let's look at X. X has proton number. This is a graph of neutron number against proton number. So X has proton number of 94 and the nucleon number is 94 plus 145. 94 plus 145 to get the number of nucleons. So there are 239 nucleons. So let's find the alpha particle. So this decays by emission of an alpha particle, which is 42. Give us a new nucleus Y, whose nucleon number is 239 minus 4, which is 235. And the proton number is 94 minus 2, which is 92. So the number of neutrons is going to be 235 minus 92. 235 minus 92, which is 143. The number of neutrons should be 143. So proton number should be 92. 92. Neutrons should be 143. So the answer is B. The nuclei of common isotopes of hydrogen, helium, lithium, and beryllium are shown. Which nucleus contains equal numbers of up and down quarks? So hydrogen, that is 1 proton, 0 neutron. 1 proton, 0 neutron. Helium, those are 2 protons and 2 neutrons, because it is 4 minus 2, which is 2. Lithium, those are 3 protons and 7 minus 3, that is 4 neutrons. 4 neutrons. Beryllium, 4 protons, 9 minus 4, that is 5 neutrons. So which nucleus contains equal numbers of up and down quarks? So this one has 1 proton, those are 2 up quarks, and 1 down quark. 2 up, 1 down. Then this one has 2 protons, those are 6 up and 6 down. Because 2 protons, that is 2 times up, up, 2 into up, up, down, plus 2 for 2 neutrons, that is 2 into up, down, down. So up is 2 times 2, that is 4, plus 2, that is 6 up. For down, it is 2 times 1, that is 2, and then 2 times 2 down, that is 6. So there are 6 up and 6 down for alpha particle. Then we can check for lithium. Lithium has 3 protons, that is 3 into up, up, down, and 4 neutrons, which is 4 up, down, down. This one gives us 6 up and 3 down, plus this one gives us 4 up and 8 down. So total number of down is 10, total 10 up and 11 down, so they are not equal. You can also verify for beryllium. 4 protons, that is 4 into up, up, down. 5 neutrons, that is 5 into up, down, down. So 4 up, up, those are 8 up, plus 5 up, that is 13 up. 4 times down, that is 4 down. 5 times 2 down, that is 10 down, plus 4, that is 14 down. So the only nucleus is going to be helium with 6 up and 6 down quarks. A nucleus of uranium-235 undergoes a series of decays. During the series of decays, 2 alpha particles and 1 beta minus particle are emitted. As a result, a nucleus of actinium Sc is formed. What is the correct notation for the nuclide of actinium that is formed? So we just need the proton number and the nucleon number. So uranium-235 92 decays to give us Sc plus. During the series of decays, 2 alpha particles are emitted, so I'll say 2 times alpha for 2 plus 1 beta minus, so 1 beta minus 0 negative 1. So the proton number should be 92 on both sides. So this side we have 92 on the left. The other side we have 2 times 2, that is 4, minus 1, that is 3. So 92 minus 3, that is going to be 80. 92 minus 3, that is going to be 89. So this is 89. And then the nuclear number have 2 times 4, which is 8. So 8 minus subtract from 235. 8 subtract from 235 minus 8, that is 227. So the nuclear number here is 227. So we have just ensure that the nuclear number is balanced or the nuclear number is conserved. Therefore, our answer is going to be B. Which particle is a fundamental particle? It should not be broken down any further, and that is the electron. The hadron is not a fundamental particle because hadrons are made up of quarks. The neutron is made up of quarks, and the proton is made up of quarks, so they are not fundamental. A nucleus of magnesium decays into a nucleus X by emitting a beta plus particle. The decay is represented by the equation shown here. What are the values of P and Q? So we just balance. Then beta plus is not changing the nuclear number, so P must be 23. So we eliminate 22, we remain with the C and D. Then the proton number must reduce, because on the left it is 12, so 12 is going to be equal to Q plus 1, which means Q is going to be equal to 11. So the answer here is going to be C. In beta minus decay, a neutron inside a nucleus changes to a proton. Which statement describes the quarks? So a neutron is changing to a proton. A neutron has up, down, down quarks. These change to up, up, down. So a down quark is changing to an up quark. So which statement describes the quark composition of the nucleus during the decay? The number of down quarks decreases by 1. I think that is true. The number of down quarks increases by 1. That is not true. They decrease. The number of down quarks stays the same. They change. The number of up quarks stays the same. They increase. So the answer is A. A beam of alpha particles is incident on a thin gold foil. One alpha particle collides head-on with the gold nucleus and is deflected back along its original path. Which statement could explain why the recoil speed of the gold nucleus is small compared with the recoil speed of the alpha particle? I think that one is easy. We said most of the mass of an atom is concentrated in a small positively charged nucleus. So, number one, most of alpha particles are slightly deflected as they pass through the gold foil. That one does not answer that question. The alpha particle and the gold nucleus repel each other. It is true, but that does not answer that question. They want which statement could explain why the recoil speed of the gold nucleus is small compared with the recoil speed of the alpha particles. The mass of the gold nucleus is much greater than the mass of the alpha particle. That is very true. If you're a chemistry student, gold is Au, and I think the proton number of the gold nucleus, the proton number of gold is greater than that of an alpha particle. So gold, the mass of the gold nucleus is much greater than the mass of the alpha particle. So the mass of the alpha particle cannot will have a smaller momentum than, the gold nucleus will not experience a greater change in speed compared to the alpha particle if conservation of momentum is to be there. The gold nucleus, which has a large mass, will have a smaller recoil speed. The alpha particle, which has a smaller mass, will have a greater recoil speed. A hadron is composed of 3 quarks. The hadron has a charge. There are 3 quarks and it has a charge. Let's check. What is the possible quark composition of the hadron? Down, down, up. Let's check the charge. Minus 1 over 3e, minus 1 over 3e. Up is plus 2 over 3e. And the total charge here is 0. When you add, down, up, strange. Down is negative 1 over 3e. plus 2 over 3e for up minus 1 over 3e for strange. And that is still 0. There is no charge. Up, strange, strange. Up is plus 2 over 3e. Strange is minus 1 over 3e. Strange again minus 1 over 3e. That is still 0. There is no charge. Up, up, strange. Up is 2 over 3e plus 2 over 3e minus 1 over 3e. The total here is plus e. So there is a charge here. So the answer is going to be D. An isolated neutron decays to produce a proton, a beta minus particle, and an antineutrino. Which row gives the quark composition of the neutron and the proton and the type of force that gives rise to this reaction? Of course, to begin with the type of force is the weak nuclear force. The weak nuclear force is the one responsible for beta minus decay. So it means I eliminate this one, I eliminate that one, because I know that it is the weak nuclear interaction which is responsible for the beta minus decay or beta plus decay. So I remain with the B and the D. Now let's see. An isolated neutron decays to produce a proton. When a neutron decays into a proton, the quarks of the neutron are up, down, down. They change to up, up, down. So the quark composition, a neutron is up, down, down. So we look for the quarks. Down, down, up. That is still fine. Down, up, up. So the D is going to be wrong because the quarks here are down, up, up, which is not true for the neutron. It is down, down, up. So the answer is going to be B. A neutron 10 is fired at uranium-235 nucleus. The neutron is absorbed by the nucleus, which then splits to form nuclei of barium and krypton. What is the number of neutrons emitted when the uranium nucleus splits? Of course, without even a calculation, the answer is going to be D if you remember nuclear physics, but we can verify here. Uranium-235 92 absorbs a neutron. A neutron is N10, and it splits to form barium 141 56 plus krypton Kr 92 36. So we conserve nucleon number. Let's say plus neutrons. Let's say X neutrons. So this is N10. So on the left, proton number is 92. On the right, we have 56 plus 36. That is 92. So proton number is balanced. Proton number is balanced. Nuclear number on the left, it is 235 plus 1, which is 236. It should be called the nuclear number on the left-hand side, which is 141 plus 92 plus x times 1, which is x. So we have 236 minus 141 minus 92. So you see x is equal to 3. So there are 3 neutrons which are emitted. Which word equation represents beta plus decay? Beta plus decay, we know that for beta plus, we can check and see a proton changes into a neutron. This gives us beta plus E0 positive 1 to balance. When a neutron changes to a proton, 10 1 1, this gives us E0 negative 1. When it is beta plus, that is E0 positive 1, this is accompanied by a neutrino. When it is beta minus, this is E0 negative 1, this is accompanied by an antineutrino. So let's check. We want beta plus, which is the one on top. So a proton P11 changes to a neutron to give a beta plus, which is a positron, plus a neutrino. So proton changes to a neutron plus electron It is not an electron. Proton changes to a neutron plus electron. It is not an electron. Proton changes to a neutron plus a positron. That is true. But this is accompanied by a neutrino, not an antineutrino. So that is not true. Proton changes to a neutron plus a positron plus an electron neutrino. That is true. So the answer is D. C is for neutron changing to, actually it is not even neutron changing to a proton. This is not true. Two alpha particles with the same kinetic energy are moving towards and are then deflected by a gold nucleus. Which diagram could show the paths of the two alpha particles? So you notice that this one is going to be closer, so it undergoes more deflection compared to the other one. The one which is further goes through a smaller deflection than the one which is closest. So it means this is wrong, and this is wrong, so the answer is going to be D. The one which gets closer undergoes a greater deflection. The one which comes close to the nucleus undergoes a greater deflection. It undergoes a greater deflection than the one which is further away. So the answer is going to be D, straight away. The equation represents the decay of a nucleus X to a nucleus Y. What are particles P and Q? So we see that proton number has reduced by 1. Proton number is reduced by 1, so P must have a 1 there. P must have a 1. And the nuclear numbers remain the same, so P has 0 on top, so this is a positron. That is a positron or beta plus. So that one is P, B is beta plus. So this one and this one are wrong. We remain with the C and D. Then Q. Because the proton number is already balanced, the nuclear number is already balanced, Q has 0 nuclear number and 0 proton number. So Q should, beta plus is accompanied by actual neutrinos. So the answer here is going to be D. Beta plus is accompanied by a neutrino. Which row gives the correct type and quark composition of the named particle? Particle neutron, it is a hadron, which is true. Particle neutron is a lepton. Neutron is not a lepton, that is not true. Particle proton is a hadron, that is true. Particle proton is a lepton, not true. So we remain with A and C. A proton cannot be a lepton, a neutron cannot be a lepton. Now let's look at the quark composition. A neutron is, they are said up, up, down, which is not true. A proton up, up, down, that is true. So the answer is going to be C. The table lists the nucleon number and proton number of various nuclei. The nuclei are represented by the letters L to M, L to T. Okay. Which row in the following table correctly shows 3 nuclei of the same element? Same element means they should have the same proton number and the 3 nuclei that have the same number of neutrons. Same element, same proton number. So let's look for same proton number. We have L, M, N. These ones have the same proton number. They have the same proton number. And then 3 nuclei of the same element, that is L, M, N. So we can eliminate here. So whatever is not L, same element is L, M, N. So this one is not the same element, not same element, because let's check. Oh no. They all have 3, they are 3 with the same proton number, so we can't conclude on that. We have also to check the neutron number now. Our neutron number, we just go on subtracting 227 minus 89. This one is 138. 226 minus 89, 137, 225 minus 89, 136, 227 minus 90, this is 137, then 226 minus 90, 136, and 225 minus 90, that's 135. We can also check these ones. 227 minus 91, that is 136. 226 minus 91, 135. 225 minus 91, 134. So they want 3 nuclei of the same element. That means they should have the same proton number, and 3 nuclei that have the same neutrons, same number of neutrons. So let's check. Those with the same number of neutrons, we have M, Q, same number of neutrons, we have M, O, those ones are 2. They are supposed to be 3. Then we have L has 138 is alone, N has 136, P has 136, and R. So we have N, P, and R. These ones have 136 neutrons. Okay, so let's see the options available. Same element, same number of neutrons. So we have seen it is NPR with the same number of neutrons. So the answer is A. Those with the same element, they have the same proton number. That is L, M, and N. But of course, we needed a row which has also the same number of neutrons, which is R, P, and N. Okay. A radioactive nucleus is formed by beta minus decay. The nucleus then decays by alpha emission, which graph of nucleon number N plotted against proton number Z shows beta minus decay followed by the alpha emission. So let's first see. A nucleus X decays by emission of a nucleus Y. So if this is Z, proton number should be Z plus 1, because the beta minus is going to be 0, negative 1. So proton number increases by 1. Let's check. So here the proton number is a decrease. It decreases from 93 to 92. So this is a decrease. That is wrong. Here the proton number is an increase from 91 to 92. That could be correct. Let's maintain that first. Here proton number decreases from 92 to 91. That is a decrease. It must increase. And here proton number also decreases, yet it is supposed to be plus 1. So the answer is going to be B without even any further calculation. The answer is going to be B because the proton number increases by 1, Z plus 1. What are the structures of the proton and of the neutron in terms of quarks? A proton has 2 up quarks and 1 down quark. So proton, 1 up quark. So these ones are wrong because the proton has 2 up quarks. Then we look at C and D. It has 2 up quarks and 1 down quark. And I think the answer is C. It has 2 up quarks, 1 down quark, and neutron has 1 up quark and 2 down quarks. In a television program to illustrate scientific models, a presenter fires a gun many times at a ball of hair. or bale of hay. Two small cannonballs are embedded within the hay, some distance apart from each other. The hay belly measures approximately 2 meters by 2 meters by 2 meters. That is, it is cubical. And the cannonballs are made of iron, approximately spherical and about 5 centimeters in diameter. What might the presenter be illustrating? So, of course, first of all, they are saying the cannonballs are made of iron, approximately spherical. So it means they are identical. Okay, that's number one. And the hay bale measures approximately 2 meters by 2 meters by 2 meters. The presenter fires a gun many times at a bale of hay. So the presenter is firing a gun at a bale of hay. It is equivalent to uh, projecting alpha particles towards the gold foil. So they are saying two small cannonballs are embedded within the hay, some distance apart from each other. Some distance apart from each other. So this is actually alpha particle scattering experiment. It's trying to demonstrate alpha particle scattering experiment. It's not referring beta decay, because beta decay does not involve firing anything towards. It is the beta particle is the one which is emitted. Here, alpha scattering experiment, alpha particles are directed towards the gold foil. So that is alpha particle scattering experiment. A certain nuclide uranium-235 has nucleon number 235, proton number 92, and neutron number 143. Data of 4 other nuclides are given below. Which nuclide is an isotope? We look at the proton number. Isotope, proton number. Which nuclide is an isotope? So 235 has proton number 91. The other one had proton number 92. So we need a nuclide with the proton number 92, and that is B, because an isotope has the proton number is the same, so that is B. During beta minus decay, which change takes place to the quark composition of the nucleus that emits beta minus particle, and which other particle is emitted? So during beta minus decay, a neutron is going to change into a proton. A neutron is written as 1, 0, a proton is 1, 1. To balance this equation, we add beta minus, which is 0, negative 1. A beta minus particle is an electron, which is accompanied by an electron antineutrino. So they said which other particle is emitted. So which change takes place? Because it is a neutron which is up, down, down, changing to up, up, down. So a down quark changes to up. We eliminate this one and this one. We have down to up, but then an electron antineutrino is emitted. So the answer here is going to be A. A nucleus of uranium-238 decays in a series of steps to form a nucleus of lead-206. An alpha particle or a beta minus particle is emitted during each step. What is the total number of beta minus particles that are emitted? We have answered this question. So what determines the nucleon number is the alpha particle, and an alpha particle is 4, 2. It is the nucleon number which determines it's the alpha particle which determines the nucleon number. So let us say uranium 238 92 emits X alpha particles. Let's say the series involves X alpha particles, 42 plus Y beta particles, that is beta 0 minus 1, then plus lead, which is PB. You don't need to know the symbols of these, but since they are given 206, 82. So we can find how many alpha particles by looking at the nucleon number. So 238 is equal to 4x plus 206. What is x? X is 238 minus 206 divided by 4. So x is 8. So we can predict that there are 8 alpha particles. There are 8 alpha particles. Then how many now beta minus particles are emitted? So now that I know x, I can now predict the total number of protons. So proton number is 92 on the left hand side. On the right hand side will be x times 2, which is 8 times 2, that is 16, and plus y minus y times negative 1, that is minus y, plus 82 of the product. So I just find y. 92 minus 16 minus 82. That's negative 6. So negative y is equal to negative 6. Negative 6 is negative y, so y is 6. So the answer is 6. There are 6 beta minus particles. Which statement about alpha particles? Which statement about alpha particles is correct? Alpha particles emitted from a single radioactive isotope have a continuous distribution of energies. That is not true. That one is only true for beta minus particles. They are emitted with a range of energies. Alpha particles have less ionizing power than beta. That's not true. They have a greater charge. Ionization will depend on the charge. The charge of an alpha particle is positive. That is the charge of a beta positive. The charge of an alpha particle is positive 2e, which is 2 times 1.6 times 10 power negative 19 coulombs. So that is also not true. The speeds of alpha particles can be as high as 1.5 times 10 power 7 meters per second. The speed of alpha particles can be as high as 0.055 c, which is 0.055 times c is 3.0 times 10 power 8. Let's verify. 0.055 times 3 exponent 8. So that is 1.65 times 10 power, this is 367. So that is correct. It is approximately this power of 7. The nuclear equation shown has a term missing. We are seeing it is beta minus particle which has been emitted. Beta minus is accompanied by an antineutrino. What is represented by the missing term? That is automatically an antineutrino. Which particle is a fundamental particle? That is an electron. The hadron is not, a neutron is not, a proton is not, because a hadron has 3 quarks, a neutron has quarks, a proton has quarks. These ones have quarks. Which elementary particle is a lepton? This one is a hadron, the neutron is a hadron, an electron is a lepton. A quark is not a lepton. How many down quarks are in a nucleus of hydrogen? Let's check. It is H31, 1 proton plus 2 neutrons. 1 proton is up, up, down. 2 neutrons is going to be up, down, down. Let's add the total. These are 2 up plus these 2 up. So those are 4 up. Let's check it down. This is 1 down plus 2 times these 2, that is 4. So it is 1 down plus 4 down, which gives us 5 down. So the answer is D. There are 5 down quarks. What is the correct equation for beta plus decay? For beta plus, we say the neutron N10 changes into a proton P11 plus beta plus, which is 01. No, it is the other way around. Because it is beta plus, it is a neutron changing to a proton. because the equation is not balancing. So it is a proton P11 changing into a neutron N10 plus beta plus, which is 01. Now it is balancing, and this is accompanied by a neutrino. Because it is a positron, so it is accompanied by a neutrino. So proton, this is wrong, this is wrong. It is proton changing to a neutron, giving us a positron and an electron neutrino. So the answer is D. In the alpha scattering experiment, a beam of alpha particles is aimed at a thin gold foil. Most of the alpha particles go straight through or are deflected by a small angle. A very small proportion are deflected through more than 90 degrees, effectively rebounding towards the source of the alpha particles. Which conclusion about the structure of the atoms cannot be drawn from this experiment alone? Mass of the atom is empty space, that one can be drawn from it. Most of the mass of the atom is concentrated in the nucleus, that one can be drawn from it. The nucleus contains both protons and neutrons. We cannot come up with this conclusion from the alpha particle scattering experiment alone. Another experiment needs to be used to confirm that both protons and neutrons exist. The nucleus is charged, that one can be confirmed by the deflection. So the answer here is C, cannot be drawn from this experiment. Radon 211, francium 210, and radium 212 are three nuclides. How many neutrons does each nuclide have in its nucleus? We want the number of neutrons. We just subtract. 211 minus 86. That's 125 for radon. 125. So I think the answer is going to be B. The answer is going to be B. I can check the rest. The other one is 210 minus 87. That's 123. The other one is 212 minus 88. That's 124. So the answer is B. A neutron is composed of one up quark and two down quarks. When the neutron decays to a proton, there is beta emission. What is the change in the quark structure of the neutron due to beta emission? So a neutron changes when the neutron decays into a proton. A neutron is N10, proton is 11. So we balance the proton number. This gives us beta as 0, -1, so the total proton number is 0 on both sides. So this is a normal electron which is accompanied by an antineutrino. So this makes the answer to be, so this is up, down, down, changes to up, up, down. So a down quark changes to an up quark. So we have down to up. This one and this one are wrong. Then down changes to an up quark plus beta minus, and beta minus is accompanied by an antineutrino. So the answer is going to be B. A nucleus of magnesium undergoes beta plus decay, as represented by the nuclear equation. What is nucleus X? So let's balance. This one, of course, has 0, 0. Beta plus is 0, 1. Proton number here will be 12. This will be 11, so that 11 plus 1 is 12. So we have eliminated this one, we have eliminated that one. The nucleon number does not change, it remains 23, so the answer is going to be C. The nucleon number is 23. Which list contains only leptons? We go through the list: electron, neutrino, positron. Those are leptons. Electron, neutrino, proton. The proton is not a lepton. Electron, proton, neutron. Proton and neutron are not leptons. Neutrino, yes. Neutron, no. Positron, yes. So the answer is going to be A. An element has two isotopes, isotopic forms. What are the nuclear arrangements of these two isotopes? An element has two isotopic forms. What are the nuclear arrangements of these two isotopes? Remember, isotopes have the same proton number. They have different nucleon number and different proton number. That's not true. They have different nucleon numbers but the same proton number. That is true. They have the same nucleon number and the same proton number. It is not possible to have the same nucleon number and the same proton number. They have the same nucleon number but different proton number. That one does not make them isotopes. A hadron has a charge positive E, where E is the elementary charge. Which combination of up and down quarks could form this hadron? So just check the charges. Down, down, down is going to be negative 1 over 3e minus 1 over 3e minus 1 over 3e, which is a negative charge. So this is negative e. Up, down, down is 2 over 3e minus 1 over 3e minus 1 over 3e, which charge is 0. Up, up, down is 2 over 3e plus 2 over 3e minus, because down is negative 1 over 3e. That is, this gives us positive e. Up, up, up. Up, up, up is 2 over 3e plus 2 over 3e plus 2 over 3e, which gives us positive 2e, because that is 6e over 3, which is positive 2e. So the answer is going to be C. Positive, the charge is positive e. Okay. An unstable nucleus goes through successive decays to become a final stable nucleus. An initial nucleus and the final nucleus are isotopes, so they have the same proton number. How many alpha and beta minus particles could have been emitted during the decay sequence? So we said in one of the numbers that if X is Az and their isotopes, Y should have the same proton number Z, so plus alpha particles, which is He42. Let's say the number of alpha particles is X plus beta minus. So beta minus is 0, -1, that is Y. We have said if Z remains the same, it means Z is equal to Z plus 2X minus Y, which means Y is always going to be twice X. In other words, the number of beta particles will always be twice that of alpha particles. Let's check. If alpha is 1, here it is showing beta is 0, which is not true. If alpha is 1, here it is showing beta is 2, which is possible. If beta is 1, if alpha is 1, beta is 2, so that is Y is equal to twice X. If alpha is 2, beta is supposed to be 4. If alpha is 2, beta would be 4, but here they are saying it is 0, which is not true. And this is 1, so the answer is going to be B. A hadron has a charge of -E and is composed of 3 quarks. What could be the quark composition of the hadron? The charge is negative. You just check the charges. Strange is -1 over 3e. Because there are 3, I'll multiply this by 3. Total charge is going to be -E. I think that is enough. The answer is going to be A, because it's -E. You can check the B. Up is 2 over 3e plus, they are 2 strange, so I'll say 2 times -1 over 3e. So 2e over 3 minus 2e over 3, that is 0. Here up there are 2 up, so 2 times 2 over 3e plus negative or minus -1 over 3e. So this is 4e over 3 minus 1 over 3e, which is which is positive E. Up, 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 those are 3 into 2 over 3E, which gives us positive 2E. So the answer is A. Radiation from a radioactive source has a range of a few millimeters in air and can be deflected by electric fields. A few millimeters in air can be deflected by electric fields, so it has charge. We eliminate gamma. It has a range of a few millimeters in air, that is automatically alpha radiation, because the range of beta particles in air is approximately 2 meters. Which equation describes the process of beta plus decay? Beta plus, we know beta plus, if it is beta plus decay, a proton changes into a neutron. So a proton, so this is plus beta plus, which is 0, 1. So beta plus is accompanied by, because it is an antiparticle, it is accompanied by an electron neutrino. So up, up, down changes to up, down, down, plus these particles. So we'll eliminate these two. We have those two. So up, up, down changes to down, down, up, plus beta plus, but is accompanied by a neutrino, which makes the answer to be C. The answer there will be C. An astatine nucleus has a nucleon number 218 and a proton number 85. It decays to form a polonium nucleus emitting beta minus particle and an alpha particle in the process. What are the nucleon number and proton number of this polonium nucleus? So we have astatine, I don't know whether it is SC, but that one doesn't matter. 218, 85. It is emitting alpha. Alpha is 42. Beta, beta minus, that is 0, negative 1, plus another nucleus Y. We balance, nucleon number will be 218 minus 4, which is 214. So we have eliminated the C and the D. Proton number, this side it is 85. This side is 2 minus 1, which is actually 1. So the other side will be 84. So this will be 84. 84 plus 2, 86 minus 1, 85. So the answer there is B. What is the quark composition of a hydrogen 31H? H31. We have answered this. Quark composition, it has one proton, that is up, up, down. And then 3 minus 1, those are 2. 2 neutrons. 2 neutrons, which is twice up, down, down. So we have 2 up plus 2 up, those are 4 up. Then 1 down plus 2 times 2 down, that is 5 down. This is 1. This 2 times this 2, this gives us 4 down. So 1 down plus 4 down, that is 5 down. So 4 up and 5 down. The diagram shows a sequence of radioactive decays involving 3 alpha particles and a beta minus particle. Okay, what is nuclide T? Let's first find nuclide Q. Alpha is 42. So the proton nucleon number reduces by 4, which makes this one 233. Proton number reduces by 2, which is going to make this one 91. Beta minus is 0, negative 1. Proton number increases by 1, which makes this one to be, this one is going to be 92, and nucleon number remains 233. S alpha particle reduces the proton number by 4, which makes this one to be 229. Proton number reduces by 2, which makes this one to be 90. Again, alpha nucleon number reduces by 4, which is 225. Proton number reduces by 2, which is 88. So the answer is going to be A. Which combination of up and down quarks forms the neutron? The neutron is up, down, down. So the answer is C. Each option shows the number of neutrons, protons, and electrons in two atoms, some of which are ionized. Which pair of atoms in the table are isotopes of the same element? Same element, they should have the same proton number. They should have the same proton number. So they say each option shows the number of neutrons, protons, and electrons in two atoms. Atom 1, it has this one has 20 protons, 20 neutrons, the other one has 20 neutrons. One has 17 protons, the other one has 19 protons. So these are not isotopes, so we ignore this one. We go to the next one. The same number of neutrons. This one has 23 protons, the other one has 24 protons. These are not isotopes because the proton number is not the same. 34 neutrons, 36 neutrons, the other one has 29, 29. These are same number of protons, so those are isotopes. So the answer is C. Which combination of up quark and down quarks forms a proton? A proton is up, up, down, so that is B. A nucleus emits a beta minus particle. What is the change to the proton number and to the nucleon number of the nucleus? Beta minus. So a proton, a neutron N10 gives us a proton P11 plus beta minus, which is 0, -1. So the proton number increases by 1, the neutron number decreases by 1. So proton number is +1, nucleon number, oh, so what is given here is nucleon number, not neutron number. So proton number increases by 1. But since the neutron number reduces by 1, the nucleon number does not change. So the answer here is going to be D. This is nucleon number, not proton number. So since the proton number increases by 1, the nucleon number decreases by 1, total number of nucleons does not change, so it remains the same. So that means the answer here is going to be D. How many up quarks and how many down quarks are in a nucleus of chlorine 3717? So there are 7 protons plus number of neutrons is 37 minus 17, which is 20 neutrons. So number of protons is going to be 17. I mean the quarks in protons, that is up, up, down. And for neutrons, we have 20 into up, down, down. So total up quarks is going to be 17 times 2 because there are 2 here plus 20 times 1, 20 times 1, that is up. So these are up quarks. Down quarks, we have 17 times 1 plus, there we have 20 times, there are 2 here. So times 2. So 17 times 2 plus 20, there are 54 up quarks. And 17 plus 40, there are 57 down quarks. So 54, 57, the answer is B. A proton in a nucleus undergoes beta plus decay. One of the products is a neutron. What are the other products? A proton will now change into a neutron 1, 0 plus beta plus, which is 0, +1. Of course, a positron is accompanied by a neutrino, an electron neutrino. So it is a positron and an electron neutrino. Positron, neutrino, that is C. A certain type of hadron has zero charge. It is composed of a down quark, a strange quark, and one other quark. What could be the other quark? So charge is zero. So zero charge is equal to total charge. Down is negative 1 over 3e. Strange is negative 1 over 3e plus the charge of the other quark. So you notice that 0 is equal to negative 2 over 3e plus q. So the charge q is equal to 2 over 3e positive. This could be charm top up. So the answer is up. A neutron collides with a nucleus of uranium-235. One possible nuclear reaction that results in is represented by that equation, where X represents one or more particles. What does X represent? Let's try to balance the equation. Here proton number is 92, and here it is also 92. So proton number for X could be 0. Then nucleon number, so proton number is going to be 0. The nucleon number on here it is 236, 235 plus 1, that is 236, is equal to 154 plus 80 plus those of X. So we have 236 minus 154 minus 80. That is 2. So X is going to be 2 neutrons because it has no nucleon number. So this is going to be 2 neutrons. It can't be 1 neutron because we have got a 2. It can't be electrons because the charge is not, there is no charge there. So there are actually 2 neutrons. A nucleus Q has the notation QYX. Which of the following is an isotope of Q? Same proton number. So the answer is automatically A. Same proton number, that is an isotope. In beta minus decay, a neutron inside the nucleus changes to a proton. Which statement describes the charge? So it is a neutron which is up. Which statement describes the quark composition of the nucleus during the decay? So it is a neutron changing. So a neutron is up, down, down is changing to up, down. So it means the number of down quarks decreases as the number of decreases by 1 as the number of up quarks increases by 1. So the answer is going to be A. The number of down quarks decreases by 1 because up, down, down changes to up, up. The number of down quarks increases by 1. That's not true. The number of down quarks stays the same, it changes. The number of up quarks stays the same, it changes. So the answer is A. Which statement about two nuclei that are isotopes of the same element is correct? Remember, isotopes must have the same proton number. And if they have the same proton number, then they can have the same number of electrons if they are uncharged. Because the number of protons dictates the number of electrons for a neutral atom. So the nuclei have the same acceleration when in the same uniform electric field. Okay, same acceleration. The nuclei each have the same number of neutrons. The nuclei have each of the same number of nucleons. Uncharged atoms containing the nuclei each have the same number of electrons. Same number of electrons will imply same number of protons. So those are isotopes. Therefore, the answer is going to be D. In a nuclear physics experiment, a nucleus S3216 collides with a nucleus of MO 9442. The nuclei combine together and immediately emit a single alpha particle. The nuclear reaction is shown here. What is X? So alpha particle is 4, 2. So proton number on the left hand side is 32 plus 94. So we subtract 4. So that is 122. So proton number is 1, nucleon number is 122. So these ones are wrong. So the answer is strictly A. Which diagram represents the quark composition of an antineutron? An antineutron is an antiparticle. It is made up of antiquarks. These ones are quarks, so these ones are wrong. Then a neutron has up, down, down. So an antineutron should have anti-up, anti-down, anti-down. So the answer is going to be A. What is a conclusion from the alpha particle scattering experiment? Protons and electrons have equal but opposite charges. That is not a conclusion from the alpha particle scattering experiment. Protons have a much larger mass than electrons. We can't conclude that from the alpha particle scattering experiment. The nucleus contains most of the mass of the atom. That one can be concluded from the alpha particle scattering experiment. The nucleus of an atom contains protons and neutrons. This one cannot be concluded from the alpha particle scattering experiment alone. Further experiments should be carried out to come up with that conclusion. But the nucleus contains most of the mass of the atom can be concluded by the alpha particle scattering experiment. Which particle is a hadron? Remember, hadron must have quarks. The lepton has no quarks, neutrino has no quarks, the positron has no quarks, so the answer is D. The table contains data for 4 different nuclei, P, Q, R, and S. P, Q, R, and S, which 2 nuclei are isotopes of the same element. So isotopes should have the same proton number. They have given us number of neutrons and number of nucleons. We can find the number of protons. For P, proton number is 10 minus 5, which is 5. For Q, proton number is 10 minus 6, which is 4. For R, proton number is 14 minus 6, which is 9. No, it is 8. Then for S, 16 minus 8, which is also 8. So R and S are going to be isotopes because they have the same proton number 8. So that is R and S. Which particle is a fundamental particle? A fundamental particle should not be broken down any further. It should be the simplest. So alpha particles have protons, neutrons with quarks. An electron has nothing. Neutrons have up, 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 down, down. Protons have up, up, down. They have quarks. So the answer is the electron. A sample of an isotope emits beta minus particles. The beta minus particles have a range of energies. What must also be emitted? That is, beta minus is an antineutrino, beta plus is a neutrino. So the answer here is simply going to be an antineutrino or antineutrinos. Antineutrinos accompany beta minus, the neutrinos accompany beta plus. A nucleus of magnesium decays into a nucleus of sodium by emitting a beta plus particle. The decay is represented by this equation here. What are the values of P and Q? We just balance. So on the left hand side we have 12 for protons, Q plus 1. So Q is going to be 11. We eliminate B and D. Then we remain with 23 equals to P plus 0. So P is 23. So the answer is going to be C. Thorium decays by beta minus emission into a daughter product, which in turn decays by further beta minus emission into a granddaughter product. Which letter in the diagram represents the granddaughter? So let's first say thorium. It is 23490. It is emitting the first daughter, which is plus beta minus 0, negative 1. So this is going to be 91 to balance the proton number, and this will remain 234. Then this one, Y234 and 91, again decays to give a beta minus. Let's say it gives us X plus beta minus again. So this remains 234, and this will be now 92. So the answers should not be along C and D, because it should be 92. Proton number should be 92. But now, how about the nucleon number? We have seen the nucleon number will be 234. So the answer is going to be B. Which statement describes beta minus decay in terms of a simple quark model? Remember, beta minus decay, a neutron N10 decays to give a proton P11. This must be accompanied by beta minus, which is 0, -1, plus an electron is accompanied by an antineutrino. So a neutron has up, down, down. It changes to a proton, up, up, down. So down quark changes to an up quark. So these two are C and D are wrong, because C and D are saying an up quark changes to a down quark. Then A is saying a down quark changes to an up quark and emits an electron and an electron antineutrino. I said a beta minus is accompanied by an antineutrino, so the answer is going to be A. Which word equation represents beta plus? Which word equation represents beta plus decay? Beta plus, a proton P11 changes into a neutron N10 plus beta plus, which is 0, +1. A beta plus is a positron. This is a positron, which is accompanied by a neutrino or an electron neutrino. So a proton changes into a neutron. Proton changes into a neutron plus a positron, not an electron. So these two are wrong. It gives us a positron, but a positron is accompanied by a neutrino. So the answer is going to be D. Which statement about the alpha scattering experiment provides evidence for the existence of the nucleus? Existence of the nucleus, that must be deflection. And the first one is saying a tiny proportion of the alpha particles are deflected through large angles. The answer is going to be A. Slower alpha particles are deflected through large angles. That cannot be possible. The kinetic energies of the deflected alpha particles are unchanged. This cannot give that conclusion. Does not provide evidence for the nucleus. The number of alpha particles deflected depends on the thickness of the foil. This one does not give evidence of the existence of the nucleus. The gold nucleus Au 18579 undergoes alpha decay. What are the nucleon number and proton number of the nucleus formed by this decay? So we have Au 18579 undergoes an alpha decay. It emits alpha 42 plus a new nucleus. Let me call it X. Proton number will therefore be 181. Nucleon number, and proton number will be 77. So proton number is 77. We ignore these two. Then nucleon number is going to be 181 minus 77. So one nucleon number is 181. They want nucleon number. So the answer is going to be C. Which row gives the correct classification of protons, electrons, and neutrinos? Protons, electrons, and neutrinos. Of course, we know protons are hadrons, electrons are leptons, neutrinos are also leptons. So let's see, protons are hadrons, so this C and D are wrong. Electrons are leptons, so this one is wrong. Neutrinos are leptons, so this one is wrong. So the answer is going to be B. So protons are hadrons, electrons are leptons, neutrinos are leptons. Which equation represents beta plus? decay. We have seen that equation. We have said a neutron N10 decays into a proton P11 plus, no, it is a beta plus decay. It is a proton P11 decaying into a neutron N10 plus beta plus, which is 01. This is accompanied by a neutrino. This is a positron, which is accompanied by a neutrino. So proton changes into a neutron. These two are wrong because it's a proton changing into a neutron. To give us a positron, which is accompanied by a neutrino, the answer is D. A nitrogen-13 nucleus undergoes beta decay. In the equations below, V and this symbol here and this one represents a neutrino and an antineutrino respectively, and gamma represents the photon of gamma radiation. Which equation represents this decay? So it is undergoing a beta decay. So we can just verify whenever beta minus is emitted, it is accompanied by an antineutrino. So first of all, let's check our proton number if it is conserved all through. This side is 7 and this side it is not conserved because this is 6 plus -1, which is 5. This is wrong. This is 7, 6 plus -1, which is wrong. This is 7, 6 plus 1, that one is conserved. 7, 6 plus 1, that is conserved. Now let's concentrate on these two. This is a positron accompanied by an antineutrino, which is not possible. A positron is accompanied by a neutrino, so the answer is going to be D. It is the electron which is accompanied by an antineutrino. Radon is the start of a decay chain that forms bismuth, I think, by alpha and beta minus emissions. For the decay of each nucleus of radon, how many alpha particles and beta minus particles are emitted? So radon Rn 22286 is decaying to give us bismuth 21483 plus X alpha particles, which is 42, plus Y beta minus particles, which is 0, -1. Note that the nucleon number, the change in nucleon number is going to be only determined by the alpha particles. So let's find X. So 222 is going to be 214 plus 4X for alpha particles. The other one is 0. So X equals 222 minus 214 divided by 4. So X is 2. So there are two alpha particles. So we concentrate on, we cross out this one and that one. There are two alpha particles. Now that we know alpha particles, we can use the number of alpha particles to determine Y by conserving proton number. On the left hand side is 86. On the right hand side will be 83 plus X is 2 times 2, which is 4, plus Y times -1, which is minus Y. So what is the value of Y? So 86 minus 83 minus 4, -1. -1 is equal to -Y, so Y is 1. So the answer is going to be B. The magnitude of charge on the proton may be regarded as +1 unit. On this basis, the charges on the up quark, down quark, and their antiquarks are not whole units. Which row in the table shows the correct values for the charges of up? Remember, up is +2/3e. Down is -1/3e. Anti-up is going to be -2/3e. Sorry, yes. Then anti-down will become +1/3e. So up, this one is correct for up. This is wrong. This is correct. These two are wrong. So we have eliminated B and D. Down Down, this is correct. This one we have already eliminated. We have eliminated these two, so we concentrate on these two. Down, this is correct. And up. And up should have a negative charge. This is wrong. This is correct. So it means we have also eliminated that one. Automatically, the answer remains C. That is up, down, and up, and down. What is a proton? A hadron, a particle consisting of two down quarks and one up quark. A positive fundamental particle, that is automatically not correct. A positive lepton, that is not correct. A particle consisting of two down quarks and one up quark, that is not correct. A proton has two up quarks and one down quark, so the answer is a hadron. It is made up of quarks. What are the correct descriptions of a gamma ray and a beta minus particle? We know gamma is electromagnetic, beta is electron, fast moving electrons. So high speed electron, that is not true for gamma. Electromagnetic radiation, that is true, but beta minus is not a helium nucleus. A helium nucleus, helium-4 nucleus, that is alpha. Gamma ray is electromagnetic, that is true. High speed electron, that is true. So our answer is going to be C. Gamma ray is electromagnetic and beta particles are high speed electrons or fast moving electrons. In a radioactive decay series, 3 successive decays each result in a particle being emitted. The first decay results in the emission of beta minus. The first decay results in the emission of beta minus particle. The second decay results in the emission of an alpha particle. The third decay results in the emission of another beta minus particle. Nuclides P and S are compared. Which statement is correct? We are comparing P and S. So let's first see. Emitting beta minus, proton number increases by 1. Emitting alpha, proton number decreases by 2. Emitting beta minus, proton number again increases by 1. So which statement is correct? P and S are identical in all aspects. Let's check. P emits, let's say this as AZ. If it emits beta minus, so this remains, Q will have A and this will be Z plus 1. If it emits beta minus, proton number increases by 1. Then Q emits alpha to form R. If it emits alpha, proton number will be A minus, nucleon number is A minus 4. Proton number will be Z plus 1 minus 2. That is R. Then this emits beta minus again to form S. So nucleon number does not change, so it will be A minus 4. Proton number will now be Z plus 1 minus 2 plus 1. So which gives us actually Z, because in other words S is going to be Z A minus 4. So they are isotopes. P and Z are isotopes. P and S are isotopes of the same element. S is a different element. S is a different element of reduced mass. So the answer is going to be B. P and S are isotopes because you see total here is Z. Total number of protons is Z. So the proton numbers remain the same. Or we have gone back to the same proton number. The calcium nuclide Ca is formed by beta minus decay. What are the nucleon number and proton number of the unstable nuclide that underwent beta minus decay to form the calcium nuclide? So the calcium nuclide is formed by beta minus decay. So let's say X is forming calcium, 42, 20 plus beta minus, which is 0, -1. So this remains 42. Nucleon number remains 42, so we eliminate A and B. Proton number is going to be 20 plus -1, so this is going to be 19. So the answer is going to be C. The answer is C. Proton number is 19, nucleon number is 42. The diagram shows the arrangement of atoms in a particular crystal. Each atom is at the corner of a cube. The mass of the atom is 3.5 times 10 power -25 kilograms. The density of the crystal is 9.2 times 10 power 3 kilograms per meters cubed. What is the shortest distance between the centers of the two adjacent atoms? Let's first find it is a cube, we find the volume. So volume is equal to, if density is mass over volume, so volume is going to be mass divided by density. So this would be 3.5 times 10 power -5 divided by the density, which is 9.2 times 10 power 3. Remember, volume is side cubed. So for the side, I'll find the cube root. The cube root of 3.5 times 10 power -25 divided by 9.2 times 10 power 3 to find the side, because volume is side times side times side. So I'm finding the cube root. So 3.5 exponent -25 divided by 9.2 exponent 3, then cube root. So this is going to give us 3.336 times 10 power -10 meters. So this is approximately 3.4. So we can take that to be the approximate shortest distance between the centers of two adjacent atoms. So the answer is going to be C. When alpha particles are directed at a gold leaf, almost all alpha particles pass through without deflection. A few alpha particles are deviated through large angles. What are the reasons for these effects? So if almost all pass through, it's because most of the atom is empty space. In other words, most of the alpha particles pass through because most of the atom is empty space. If a few are deflected, it's because most of the mass is concentrated in a positively charged nucleus. So most alpha particles have enough energy to pass through. That one is wrong. Most alpha particles miss all gold atoms. That one is wrong. The gold nucleus is very small, so most alpha particles miss all the nuclei. That is correct. Occasionally, the path of an alpha particle is close to a nucleus. That's why they undergo large deflection. So the answer is going to be C. The nuclide Rn decays in a sequence of stages to form the nuclide Pb. 4 of the nuclides formed in the sequence are alpha particle emitters. The others are beta particle emitters. How many nuclides formed in the decay sequence are beta particle emitters? So let's see. Rn 22286 is going to give us Pb 20682 plus alpha particles, because they said 4 of the nuclides formed in the sequence are alpha particle emitters. So it means there are 4 alpha particles emitted. That is 442 plus X beta particles. When we say beta particles, that is always beta minus, so 0, -1. So our task is to find X. So let's use the proton number. So on the left we have 86 is equal to 82 plus 4 times 2, which is 8, plus x times -1, that is minus x. So 86 minus 82 minus 8, that's -4. So x is equal to -4. So the question is asking us to find how many nuclides formed in the decay nucleus sequence are beta particle emitters. So since -x is equal to 4, it means x is 4. So it means 4 beta particles can be emitted. So it means there are 4 beta particle emitters. So the answer is going to be 4. An experiment in which alpha particles were deflected by a gold foil produced new insights into the structure of the atom. Which conclusion can be drawn from the results of the experiment? Atomic nuclei occupy a very small fraction of the volume of the atom. I think that is true. Electrons orbit the atomic nucleus. We can't prove this from that experiment. Some atoms of the same element contain different number of neutrons. We can't verify this from that experiment. The atomic nucleus contains protons and neutrons. We can't verify this from that experiment. So the answer is simply A. Atomic nuclei, the nucleus occupies a very tiny volume of the atom. That's why most of the atom is entirely empty space. A radioactive substance contains a number of identical nuclei that emit beta particles. Which property of these nuclei remains unaltered by the emission? A radioactive substance contains a number of identical nuclei that emit beta particles. So it means the nuclear number does not change if beta particles are emitted, because beta is written as beta 0, -1. So which property of the nuclei remains unaltered, remains unchanged? So that is going to be nuclear number, because beta is 0, -1. A uranium-238 nucleus undergoes nuclear decays to form uranium-234. Which series of decays could give this result? So let's see, uranium-238, 92 to give us uranium-234, 92. So the proton number has not changed. That means it must be beta decay. No, not beta decay. It is emitting, the proton number has not changed. Okay, let's say it emits alpha particles. Let's say it emits X alpha particles, that is 42 plus Y beta particles. When it is just beta, it is beta minus. So this is beta minus 0, -1. Let's see the number of alpha particles emitted. So 238 is equal to 234 plus X times 4, that is 4X. Y times 0. So we have 234, 238 minus 234 divided by 4. So X is 1. There is 1 alpha particle emitted. This one says 4 gamma rays. That one is wrong. 4 beta particles only. That is wrong. Let's see if there are 4 beta particles anyway. Since we know that X is 1, we can now find Y using proton number. 92 on the left hand side is equal to 92 X times 2, that means it is plus 2, and Y times -1, that is minus Y. So you see that negative Y is equal to -2, meaning Y is 2. So there are 2 beta particles. So 4 is wrong. 1 alpha particle and 2 beta particles, I think that is correct. 2 alpha particles, 8 beta particles, that is wrong. Nucleus P decays in 2 stages to produce nucleus Q. Which decay sequence will result in the highest number of neutrons in nucleus Q? Nucleus P decays in 2 stages to produce nucleus Q. Which decay sequence will result in the highest number of neutrons? An alpha particle followed by a beta particle. an alpha particle followed by a beta particle, let's see. If P decays by emission of an alpha particle, so alpha is 4,2 to produce nucleus Q. Nucleus P decays into 2 stages to produce nucleus Q. So to produce nucleus Q, and then which decay sequence will result in the highest number of neutrons in the nucleus Q. So one, we are saying an alpha particle followed by a beta particle. An alpha particle followed by a beta particle, it means the number of neutrons in the Q will reduce because the proton number reduces. If it emits an alpha particle, proton number reduces by 2, followed by a beta particle, proton number increases by 1. So it means we want the highest number of neutrons. So it means this one will have alpha particle increases by, proton number reduces by 2, then again it increases by 1. So it means, okay, then let's say an alpha particle followed by gamma radiation, proton number reduces by 2. It means the the number of neutrons has reduced. Then let's see, remember even the nucleon number, every time an alpha particle is emitted, even the nucleon number A reduces. So let me add here beta first so that people can see. So let's add beta minus, because every time they just say beta particle, it is beta minus 0, -1 plus Q. So Q will be Z plus 1, and this will be A minus 4. So proton neutron number is A minus 4 minus Z plus 1. Let's compare two alpha particles. An alpha particle followed by gamma radiation, it means P A Z will just be Q A minus 4 Z plus 2, then plus gamma, because it's an alpha particle followed by gamma. If it is a beta particle followed by another beta particle, it means P, which is AZ, will therefore be Q. A does not change, and Z, because it is accompanied by this is minus, it is not plus, minus 2. This is Z minus 2, not plus 2, because an alpha particle reduces the proton number by 2. So it is accompanied by, it is a beta followed by another beta. So this is Z is going to be minus 1, plus 1, again plus 1. Then because we have two beta particles, beta minus 0, -1, and another beta minus 0, -1. Okay, so the nucleon number has not changed, it has remained, it has not reduced. But then the proton number increased by 2. I think the answer is going to be, actually, let's check the last one, a beta particle followed by gamma radiation. So P AZ is giving us Q. A will not change. Z will increase by 1 because it is emitting a beta minus particle followed by gamma, which does not affect. So this one, the difference between A minus Z plus 1, which is the neutron number, is greater than the rest. So the answer is going to be D. A neutral atom has a nucleus given by that symbol there, CS1355. How many protons, neutrons, and electrons are in this atom? Protons are 55, so we ignore C and D. Electrons must also be 55, so we ignore, okay, they are both 55 here in A and B. Then neutrons cannot be the same as the nucleon number, so the answer is A. The nuclear equation for a fission reaction is shown in the figure here, is shown below by that equation. What are the values of x and y? So the proton number is not affected, so 92 is equal to x plus 55. Y times 0 is 0, so x is going to be 95 minus 55. Sorry, 92 minus 55. 92 minus 55, which is 37. So we eliminate D. X is 37. Then Y, we can use nucleons. 235 plus 1, which is 236, is going to be 93 plus 141 plus Y. So 236 minus 93 minus 141, so Y is 2. So the answer is going to be C. Radioactive decay is random. What is meant by random? Of course, random means we cannot predict. The decay of a nucleus can actually, we cannot predict which nucleus in a given sample is going to decay next. What does that imply? The nucleus has a constant probability of decay per unit time. The nucleus will have a constant probability of decay per unit time. We cannot predict a nucleus in a given sample that is going to decay next, but we are sure that a nucleus is actually going to decay in a given time. So the decay of a nucleus can be predicted. That's not true. The decay of a nucleus is unaffected by pressure. That one is spontaneous. The decay of a nucleus is unaffected by temperature. That is spontaneous. The nucleus has a constant probability of decay per time. That is, it has a constant decay constant. That is lambda. Constant probability of decay per time is the decay constant. The nuclei of the isotopes of an element all contain the same number of a certain particle. Nuclei of isotopes, they have the same proton number, so that is automatically D. Which statement about nuclei is correct? Different isotopic nuclei have different number of protons. Different proton number, no. Isotopes must have the same number of protons. Isotopes must have the same number of protons. For some nuclei, the nucleon number can be less than the proton number. That is not possible because nucleon number is proton number plus neutron number. In some nuclear processes, mass energy is not conserved. That is not possible. In all nuclear processes, proton number, nucleon number, momentum, and mass energy must be conserved. That means we remain with only one option, that is D. Nucleon numbers of nuclei are unchanged by the emission of beta particles. Nucleon numbers of nuclei are unchanged by emission of beta particles. That is true. If a proton changes into a neutron, the number of protons reduces, but the number of neutrons increase. One proton is lost, one neutron is gained. Total number of nucleons remains the same. The diagram shows part of a radioactive decay chain in which the nuclide thorium decays by alpha emission into radium. This nuclide is also unstable and decays by beta emission into a nuclide of actinium. This process continues. What are X, Y, and Z? Okay, so X, proton number, so it is beta, proton number has increased by 1. This is beta minus 0, 0, negative 1. So this increased by 1. X is going to remain 228. So X is going to remain 228. So we eliminate these two. Then Y, the proton number has increased by, proton number is 90 minus 89. Proton number has increased by 2. And the nucleon number, remember this was 228, has remained the same. So this must be beta particles. This must still be beta particles if the nucleon number has remained the same. So it can't be alpha. So I have eliminated Y cannot be alpha, so the answer is automatically B. A material contains a radioactive isotope that disintegrates solely by the emission of alpha particles at a rate of 100 per second. That is 100 alpha particles emitted per second. With what statement about this material is correct? The number of atoms in the material diminishes at a rate of 100 per second. That is not true. A material contains a radioactive isotope that disintegrates solely by the emission of alpha particles at a rate of 100 per second. That is 100 in 1 second. The number of atoms in the material diminishes, that is decreases, at a rate of 100 per second. That is not true. Then the number of neutrons in the material diminishes at a rate of 100 per second. That's also not true. The number of nucleons in the material diminishes at a rate of 400 per second. The number of protons in the material diminishes at a rate of 100 per second. So alpha particle is 4,2, an alpha particle is 4,2, and the mass is actually 4U. So they are saying the number of atoms in the material diminishes at a rate of 100 per second. And I'm saying that is not true. The number of neutrons in the material diminishes at a rate of 100 per second. Number of neutrons. That's also not true because it disintegrates by emission of alpha particles. So it means the number of neutrons cannot be diminishing at a rate of 100 in every second. But the number of nucleons, this is going to be the correct answer because the number of nucleons in the material is going to diminish at a rate of 400 per second because for an alpha particle, it is actually 4,2. So the number of nucleons is going to diminish at a rate of 400 per second. So the answer is going to be C. A radioactive nucleus emits an alpha particle of beta particle, creating a product nucleus. Which decay process could create the product nucleus stated? So decay of an alpha, this is 88, this is 86, it has reduced by 2. 220, an alpha is 42. So this one is wrong because nuclear number has reduced by 2. Uranium 92, 94. It has actually increased, yet it is supposed to reduce, so this is wrong. Ra 88, 87. It has reduced by 1. And 228, 228 has not changed, so this one is correct. This one could be correct, but normally when they say beta particle, it is actually beta minus. So this is supposed to be 89 instead. Then TH 90, TH 90, 231 give us PA plus beta 0, -1. So this should be 91, 231. So the answer is going to be D. Why have I rejected this one? Is because every time they just say beta particle, they are meaning beta minus. So this one is actually, it will be referring to beta plus. Two alpha particles with equal energies are fired towards the nucleus of a gold atom. Which diagram best represents their paths? Okay. So remember I said the one which is closest undergoes a greater deflection than the one which is farthest from the nucleus. So we can predict that this one is wrong because it means they are almost experiencing the same deflection. We can also predict that this one is wrong because it means the closer you come to the nucleus, the more deflected towards the nucleus it will be. Now we have two options. We have A and B. A is showing that this does not experience any deflection, yet it is close to the nucleus. Therefore, our answer is going to be C, because the one which is closest is undergoing a larger deflection than the other one, but still there is a deflection. So our answer is going to be C rather than A, because we can't say that this one does not undergo any deflection, even though it is relatively far from the nucleus. When a nucleus emits an alpha particle, how do the proton number and nucleon number of the original nucleus change? So proton number reduces by 2, nucleon number reduces by 4. Proton number by 2, nucleon number by 4. The answer is C. Lastly, for this part, the simple theory of alpha particle scattering by a thin metal foil uses the 4 assumptions given below. Which assumption is exact and is not an approximation? Each alpha particle interacts with just one nucleus. That is just an approximation. The alpha particles lose no kinetic energy when they are deflected. That is just an approximation. It is an assumption. The metal nuclei do not recoil. They can recoil. Total momentum is conserved. This one is always conserved. So that one is not an approximation. It is exact. It is not an approximation. The rest are just assumptions. That the metal nuclei do not recoil. The alpha particles lose no kinetic energy. Each alpha particle interacts with just one nucleus, which may not really be very possible. Okay, so let part 2 stop there. I will start from there in part 3. Have a blessed day. Bye bye.